Let's get started here. So this is obviously week 5 of the course. For today, you needed to examine some of the sections of or subsections of section 3. And the first subsection that you needed to examine was this section on the moving average models. And in general, we can write these moving average models as having an order of Q associated with it. And what that just basically means is that we have Q of these white noise terms, and we form a linear combination of these white noise terms with some parameters, our thetas. Eventually, actually in the next, for next week essentially, we will learn how to estimate these thetas. And so this is a formal definition now of moving average models. We've seen moving average models before, but not necessarily exactly like this. Note that we can shorten some of the notation by using what's called a moving average operator, this theta of B. With this model, please be careful about how you write it in terms of you have those plus signs in front of the thetas. Notice how that's different from if I were to write out the model as, let's say, if I were to write out an autoregressive model, I could write it like this. This is an autoregressive 1. Notice how we put a minus out in front. And this matters when we simulate data from one of these models. It matters when we ask R to give us what the ACF looks like, or now as you've seen the PACF. It matters also eventually in the next set of notes where we actually estimate these models. So we need to make sure that we get that phi right. We need to make sure that we get the theta right. It's a little bit odd to have a negative on the left side or to have this negative out in front of this phi. But just remember that if I were to rewrite the model, I would have this, where now when I take that x of t minus 1 over to the right side, which is b times x of t, I have a positive now out in front of that phi 1. So whenever I have stuff on the right side, I have that positive there. Now, with these moving average models, we looked at how to find the autocovariance function, how to find the autocorrelation function. What was one very, very, very important aspect of the autocorrelation function when we have just a moving average model? Does anyone remember? So let's say if I have a moving average 1 model.
Oh, it cuts off at the lag after 1?
Yes, exactly. So it cuts off to 0 after lag 1. In general, for moving average Q, it cuts off to 0 after lag Q. In other words, the autocorrelations are 0 after lag Q. Okay? That's a very important aspect because we, as you are starting to see now with these moving average models and also autoregressive and then ARMA models, we are going to use the ACF, characteristics of the ACF, to help us choose an appropriate model for our data. We also talked about then the concept of invertible. That basically just means that you can simply rewrite the moving average model as an infinite order autoregressive. And then subsection 3, we simply put together the AR and MA parts together. Like I said, we put them together. And so now we have what's called an ARMA model. In shorthand, we could say that this is ARMA parentheses P, comma Q, representing the autoregressive and the moving average order to our models. And again, we can rewrite the model in a very short way here using the autoregressive and moving average operators. One kind of weird aspect of these kinds of models is that we need to assume that there's no common factors. And all that basically means is this. We cannot have the following model. Notice how I have a 1 minus 0.4 times b on both the left side and the right side. Because what would happen then? I could cancel those out. And essentially, this ARMA 1,1 model becomes an ARMA 0,0 model. So this is a simple an assumption that we have to make. It's not that big of an assumption in the end. Again, there's an infinite number of possibilities of what, in this case, what phi 1 could be and what theta 1 could be. And so to not have them be exactly, essentially the same, it's not a big deal. Then with this, then we can think of our models as being causal and invertible, and we have a way to actually check that. It's actually a fairly simple way, is that we think of this autoregressive or this moving average operator as now like a polynomial. And we look for the roots of this polynomial, and that those roots, depending upon what they are, tell us if I have a causal or if I have an invertible model. And the polyroot function of R helps us do that, find those roots. Then in subsection 4, we looked at, well, how can we find the ACF for an ARMA model? And my favorite way to always do this, you saw a number of different ways. You've seen a number of different ways to do this. My favorite way is just simply rewrite everything as an infinite order moving average and then go from there. We looked at some plots of what these ARMA models would look like in terms of the ACF and how the ACF can help determine then the order for the moving average part of your model. Then in the last subsection, we introduced the partial autocorrelation function. And all this does is says, well, let me restate this. There's a nice relationship here with what you learn in a regular old regression setting. Let's say if I have a regression model that looks like this, expected value of y is equal to beta 0 plus beta 1 times x1 plus beta 2 times x2. What this beta 2 is basically representing is what's the association between x2 and expected value of y given you take into account x1. And that's essentially, and so it's a measure of association. And that's essentially what a partial autocorrelation is simply measuring. Given that, let's say that, well, yeah, I'll just leave it at that. Now, in the notes so far, we've seen the process of how to estimate in terms of the equations. We've seen the process of how to do a hypothesis test. You just haven't got to do one yet, or got to estimate one yet. That's the next subsection, and it's not that difficult. As you might expect, there's a function in R that does the calculations for us. And in fact, what's going to end up happening is this. You're going to have a plot that looks very similar to what we had for the estimated ACF. So here's positive 1, here's negative 1, here's my lag, we'll call it H, and simply we're going to look at plots that look like this. And we'll have some dotted lines that go across that are drawn at the appropriate locations so that we can do a hypothesis test. Okay? With the partial autocorrelation function, then we found out that we can use that to help us determine what P should be, the order of the autoregressive model. And this then gets into, then why do we look at the ACF? Why do we look at the PACF? Here's a nice little table that you'll see again in subsection 6 that kind of puts together some other parts of the notes that we've had previously that shows you the relationships that we have between these kinds of models and an ACF and a PACF. So what this means then in the grand scheme of things and where we're going with this is that let's say I have a data set and I do an ACF plot and I do a PACF plot. If I see something like this, the ACF tails off to 0. The PACF cuts off to 0 after lag P. Then I know I have a autoregressive model. And you could do something similar with respect to the moving average, but with the ACF and PACF behavior reversed. And then if I'm looking for an ARMA PQ model, this is the behavior that we're going to see. Tails off to 0 after lag Q, tails off to 0 after lag P. This is now when it becomes a little bit more complicated because you need to figure out where does that tailing off actually start? Is it at lag 1? Is it at lag 2? Is it at lag 3? It can be difficult, and you'll see that more in subsection 6. But at least this kind of table here gives us a starting point for potential models that we can use with our data. And then we'll have other tools that we can use to decide, should I choose this model or should I choose this model? And to relate this to other stuff that you've seen in other classes, we're going to be looking at residuals for our model to help us make this decision. We'll look at some other tools that help us measure autocorrelation. We'll look at using hypothesis tests concerning the phis and the thetas. We'll look at using the AIC as well. And so we have all these tools available to us to help come to a decision about one best model to use. Okay, so that's a brief review of the material for today. Were there any questions? Okay, let's move on to talk about project number 1. So all of you should receive your project number 1 back. The grades at the top, number of points possible out of 55, number of points earned out of number of points possible. So there was 55 points possible. The average score was good, 51.8 out of 55. Standard deviation 2.41. And overall, there was one group that got 55 out of 55. Now, so all of you have your grades. I do not post all the grades to Canvas. I do not post the grades for projects to Canvas until the very end of the semester. And I've said that before, but I just want to emphasize that. And the reason being is because it will save me a little bit of time. That if I post them all at the end of the semester, including your test grades to Canvas, rather than upload them one at a time. And again, you will know what the grades are because you will receive the graded project or the graded test back. It's just, I don't upload them to Canvas until the very end. Now, in my discussion board posts, I said to make sure that you fully see my remarks that I have on your project, I put my comments on your project using words tracking tool, so like up here, the track changes tool. To fully see my comments, make sure that you turn on all markup under the review tab. So notice how it says all markup if you see where my mouse is, right here. The reason why I say that is because I found that some students maybe are not as familiar with how to use the review or track changes tool in Word. And also the default for the track changes tool is not necessarily ideal. So just to make sure there's no confusion, here's just a graded problem from another project from another class that I had a number of years ago. And you can see in red there, those are my track changes. Those are my comments that I want you to read. So you can see obviously the student missed 1 point on this part H there. Now, the default in Word, or at least what I've always seen as the default, is that instead of having all markup here, it's simple markup. Now, look at the difference of what happens. Now, it's a lot harder to see where my actual comments are. Sure, we have some red lines on the left side that help you see it, but it's definitely not as good as if I had all markup there. So make sure for your projects, you use all markup so you don't miss anything that I have put on your project. Also, make sure you take a look at the answer key. Even if you got a problem right, take a look at how I approached it in the answer key. Because I could have approached it a different way. Oftentimes, since obviously I'm the one who's teaching this, I will have a more concise way to answer something than perhaps a student might. But also maybe even though I didn't take off points, I could have had a different answer. And so in particular, for example, I think it's, well, on number 1, when you needed to determine, based upon a plot of the data versus time, was there, is it stationary or non-stationary? And many students said non-stationary. We'll talk about more why I think a better answer would be stationary shortly. But I didn't take off points for that. And so you might be thinking, oh, I got it right. Well, yeah, you got full credit, but you didn't really have totally the correct answer. And so make sure you take a look at all problems on the project, even if you got it right. Overall, I see by me giving you the answer key, it's like the ultimate amount of feedback that I can give you, because you know what the correct answer is for every single problem. And lastly, before we get into some of the details of the project, make sure you format our code and output properly. If you might notice there might be some comments on your projects where I made some formatting changes. Please just simply implement them in the future. You can see how my answer key to how I do the formatting. And this is just done because this is the professional way to actually display our code and output. Okay, so let's talk about number one with the earthquake data. Let me pull up the answer key here. So this is the plot of the data versus time. And if you just look at where those blue dots are and the patterns that we see there, you might be thinking, okay, the mean of the series seems to be estimated to be higher there than it is here. And you may be quick to conclude, okay, I have non-stationarity in the mean because of it. In my answer, though, I said, I really don't think we do have non-stationarity in the mean. Why? Well, I have just 24 observations. Okay? Just 24. And, let's think of an extreme case. So suppose I have t here, x of t here. I have 2 points, 2 points there. Would you conclude from just those 4 observations that you have non-stationarity in the mean? I hope not. You really don't have a whole lot of information to make that judgment. It just goes, what would happen if now you went up like that? Okay, well, that totally would make you think, no, I'm okay here with stationarity. And so the problem is that if you're saying non-stationary to mean because of this, you're based upon only 4 observations. And we know, obviously, this number of earthquakes is going to fluctuate over time. And it just so might happen that because of the correlation that we have, sometimes we're a little bit up, sometimes we're a little bit up again, and then we go down. Then we go down again here. And you really don't have a whole lot of information. And that's not something I really emphasized in class before. And so that's why I was very, lenient, you could say, with respect to making this judgment. Now, when then would be a good time to make that decision that indeed that I have non-stationarity in the mean? Well, you need more evidence. You need more data that actually indicates what's going on. And so, we talked about cases like this, and this is fairly simple. And you can imagine that let's say I even have more observations where things are going up over time. That's a little bit more straightforward. But in our situation here, basically if I had, let's say, a bunch more observations here and a bunch more observations there, and sorry, I don't have a good definition what a bunch means. But if I had that, then I would say, okay, I think something's going on because over an extended period of time, it seems like this time series is up here and then it's down there. Okay? Now let's look at this a little bit further too to help emphasize the point. So what I've done here is I'm going to use the ARMA.sim function to simulate some observations. ARMA.sim is only going to be able to simulate data from a stationary series. Okay? So whatever we get here, we know it's stationary. And for ARMA.sim, I'm going to use a phi 1 equal to 0.4521. I think within the next project, you'll have some ideas why I chose that particular value without going into all the details. Notice I'm going to use exactly the same sample size as what we had. In the project, sometimes I said you only have n equal 25. I don't know why I said 25. It was actually 24. So sorry if I put that in your project. We're going to, the white noise part is going to be from a normal. And standard deviation of 1. It doesn't matter what my standard deviation here is. It's just going to change the how spread out the points are. And so let's, first of all, just set a seed. Okay. And let's simulate the data and do a plot of the time series. Okay. So we can see that those points move around over time a little bit. And we can see at about time point 19, I have a big dip that goes down. But then it starts going up. But you might be tempted, okay, well maybe right here, non-stationarity in the mean. Well, that's only 3 observations. It's really hard to make that judgment based upon that. Let's take a look at another seed and simulate observations again. Okay. Now, I think in this particular case, there really isn't evidence against non-stationarity. The points seem to be bouncing around about the same values. Let's keep on going here. Now we see a big dip down towards the bottom there, or about time 24. And that might be a little bit tempting now to say non-stationary in the mean, but we can, again, remember ARMA.sim does not generate data that's non-stationary in the mean. Let's do this one. Overall, I don't really think there's any issues with this particular plot. I mean, you might be tempted, well, now I'm a little bit high there. Well, that's only 2 observations. And one last one. Okay. And, again, you might be thinking, okay, I might be tempted to say non-stationary mean because look what's happening here. If you see where my mouse is. It seems like for about, 8 observations or so, you're a little bit lower than what you were up here. But again, this data is being generated from a stationary model. And so my whole purpose here is that, you might see things with n equal 24 in terms of saying non-stationary when that's not actually true. There's just not a whole lot of information to make that judgment. What you should do is look for much more obvious trends in making that decision about non-stationarity in the mean, rather than what we saw with the earthquakes data. Any questions about that? So, on your own, play around with this some more. Go with a smaller number of observations. Go with a larger number of observations. And that will give you a better feel about making judgments about when do I have something that's extreme enough to say, I think I have a problem. I have non-stationarity in the mean. And, to some respect, it's a matter of getting experience with this before you become comfortable with making those kinds of judgments. And this, just a little bit of a simulation here gives you some of that experience. Okay, let's see here. So then, how about we look at the same kind of case, but now where I do have non-stationarity in the mean? Yes?
Sorry, so how many time points would you say enough to say to conclude?
A bunch. Yeah, it is hard. And, perhaps what you need to do, because I was thinking about, how best to explain it. And so, the purpose of that simulation that I just showed you was, we had a few of those simulated data sets that were somewhat similar to what we had with earthquakes data. But we knew, again, that we did have stationary in the mean. And, a statistician never likes to ever be cornered into a room and told what's the sample size or how many observations do I need, and it's difficult for me to say. All I can say is that if you see it over an extended period of time, and I don't have a good definition of what extended means, we can see that with earthquakes data that was not an extended period of time. But let's take a look at now an example here where we do know that we have non-stationarity in the mean. We're going to use the same, I think I used the same sample size. We're going to use the same sample size, and let's see what happens. So if I have n equal 24, what is enough for me to say that indeed I have non-stationarity in the mean? So this is my model. Simply the first differences on the left side. Remember how we've used first differences before to solve the non-stationarity in the mean issue. But if I say my data, if I just look at x of t itself, and that's what I'm going to do a plot of, this x of t is actually non-stationary because it takes doing first differences to get stationarity. In subsection 7, if this is a little bit unclear, in subsection 7, which is for the next set of notes, this will be a little bit more clear because we're going to be talking about this kind of an aspect more. But just believe me for now, I'm going to generate some data that's non-stationary. Okay? So, all I did was I just kind of randomly picked some seeds. And these are exactly the same seeds as what I have up here. So we're going to do that seed. And don't worry about this code about how it's being simulated. Again, in subsection 7, that will make sense how this comes about. Let's take a look at the data. Well, this kind of corresponds to what I also talked about. This is obvious. We have this downward trend like that. The mean is changing as a function of time, I would think. Let's look at another example. Maybe a little bit less here than the previous one, but we do see this upward trend that seems to be continuously going, suggesting that the mean is changing. I mean, sure, like if you see where my mouse is right here, there's not really an issue, but we're going up for the rest of the series. And look how many observations this is. If we started about here at observation 8, we go to observation 24. So that was 16 observations that were in that long line there. Here's another example. A little bit less clear. If you were just to focus on where my mouse is right here, just focus on that, you probably wouldn't have a problem. We see a little bit down here. So, if I was given this data then, I would have some doubt in my mind that indeed I do have non-stationarity in the mean. I would want to see more observations to be more comfortable about it. But we do know that this model here is non-stationary. And that, again, kind of shows the problems with a small sample size. This one's fairly obvious. And one last one here. This one's not very clear. Again, if you see where my mouse is, it might be difficult to say non-stationarity in the mean. Even though we know that we do have it based upon the model that was used to generate the data. Okay? Now, suppose, so I have 24 observations here. Okay. The way that I set up this little simulation is that I can start with those 24 and keep on going, let's say to 100, to 1,000, but I'm still with the same 24. Let's see what happens if I increase my sample size. Would there be more evidence that indeed there is non-stationarity in the mean? So we'll just go immediately up to 1,000. Okay. Here we go. Same first 24 observations. Notice how we have that little observation up high first, then we go down a little bit and it seems like everything's okay. But now we can see that indeed over time, yeah, it looks like I have non-stationarity in the mean. Because I have extended periods where it looks like the series is staying in the same kind of location. Again, you can do something similar on your own as well. To this. And let me put a note to myself here. I will post this to my website, this little program that I've written. It'll be under the Section 3 materials called Week 5. Let me come back here. So one of the big things to take away here is that one should not be too picky. Look for large, obvious trends. Also, let's relate it to something that some of you have seen in another class before. So if any of you have done any kind of Bayesian modeling, what you often do is use what are called MCMC methods to simulate data from a posterior distribution, so you can use that data then to make judgments about particular parameters of interest. Now, for those of you who have had that, if you haven't had this kind of a course or haven't seen this, don't worry about it. Just ignore the next 2 minutes. So one of the big things with MCMC methods, you need to make sure that you have what's referred to in that kind of a setting, convergence. How do you make a judgment about convergence?
So I don't know, I felt like it was like at least in the class I took, it was like we look at like the chains and then we look for like the mixture of the chains or whatever.
Exactly, and I guess also I have the answer up here too. I'm sorry. We look at a trace plot, okay? And what a trace plot is, it shows you for observation 1, what was it? Observation 2, what was it? Observation 3, what was it? And all it is a plot, is a time series plot. That's all. And what you're often looking at is plots that look like this. Let's say we have T being the index of observation 1, observation 2. They're all done successively. And you're often look at plots like this. And what you're hoping is that you can kind of see what's meant to be the observations are bouncing around. You're hoping to see no trends. You're hoping to see that everything's right around the same middle point. In other words, non-stationarity in the mean. And so for those of you who've had a Bayesian class or have other experience with Bayesian analysis, when you look at these trace plots to determine convergence, you're kind of doing what we just kind of did here, looking for stationarity. What that basically means in the Bayesian context is that you're visiting all portions of the distribution. You're not going off in some weird way and being maybe stuck in a certain area of the distribution. Okay? So let's take a look at part C and D of number 1. This was a hypothesis test with the autocorrelation. And so we have this estimated ACF plot. And we can see we have this one and we have this one outside these lines that we draw on the plot to help us to determine the results of a hypothesis test. So our hypotheses are rho of H is equal to 0 versus rho of H does not equal 0. by default, these lines are drawn using alpha 0.05. Okay? For h equal 1 and h equal 9, you could say, well, you should say reject HO, because the estimated autocorrelation is outside those boundary lines. But we can see that these estimated autocorrelations are not too far outside. And in fact, for, I think it was part D, you found the p-value for this particular lag to be 0.025. So if I were to choose 0.01 as alpha instead, well, that dotted line will be above where that estimated correlation falls. And I would say don't reject in that case. And so rather than saying, yes, indeed, there is sufficient evidence to indicate the autocorrelation at lag 1 does not equal 0, what you should say instead is something like there's moderate evidence, there's marginal evidence that the autocorrelation does not equal 0. So when Sir Ronald Fisher first developed these concepts called p-values, and he suggested using 0.05 as our alpha level, his intent wasn't necessarily to make this, yes, there is evidence, no, there's not evidence, judgment. So if I have a p-value of 0.051 or p-value of 0.049, alpha 0.05, your total understanding of what's going on should not really change. You have marginal evidence. If something's going on, maybe, there's at least enough evidence here to say, hey, let's maybe go run an experiment again or go collect some more data and see if the results change. But one should not, let's say, stake their life on, p-value of 0.049, or like, yeah, I have autocorrelation. No, you shouldn't. And so be very careful about how you word these kinds of conclusions. Perhaps you've heard about this in other classes or other situations. About 5, maybe 8 years ago now, there was the whole p-value controversy was talked about. There was actually a journal in some social science that banned people using p-values because they were being misunderstood, or they didn't think that they worked, essentially. And it all comes down to fully interpreting what a p-value is representing. It gives you information about how reasonable is your observed data if the null hypothesis is true. And that's what the p-value, a probability value, is actually measuring. And you've got to be very, very careful about making such strict conclusions when you're close to what you've made as your, let's say, your cutoff, your alpha. So it's better to say marginal evidence. Now, if I have a p-value of 0.0001, then I'm saying, oh yeah, I got strong evidence. If I have a p-value of 0.09, I'd still probably say marginal evidence. If I have a p-value of 0.2, I would say, it doesn't really look like I have evidence. And so be careful with making such binary phrasing of interpretations. Okay, so let's talk about number 2 with the Shining app data. And in my notes, I sometimes talk about using this argument with PAR. X-axis equal I. Does anyone remember what that does? It basically, by default, or how R does plotting is this. Let's say it's trying to decide what should be the x-axis limits. It will look at your data relative to what's in the x, what would be plotted on the x-axis, and it will look at your data there, and it will find the minimum, it will find the maximum, and then by default, the default way that R works is it will go 4% more to the left, 4% more to the right, if x-axis is equal to R, R standing for regular. If you put I there instead, it will actually use the minimum, it will actually use the maximum itself. It will not extend out the axes. And you got to be careful when you use this. And perhaps I wasn't as careful as I should have been in describing some of this stuff to you. And so let me get the data into R. Okay. So I'm going to set this argument to be I. And actually, yeah, I'm going to set it to be I. And also, I'm going to set my x-axis limits to be 1 to 20. So lag 1 to 20. Because remember, this is with the ACF plot. Because remember, lag 0 will always be a value of 1. And often we don't want to display that. And so this is what I get for my plot. And you might be thinking, okay, everything's okay. But let me open up a new graphics window so we can compare. And suppose instead I do my x-axis limits, I start at 0.5 instead. The plot on the left is what I just got. The plot on the right is what I first did. And you can see there's a little bit of a difference for that early lag. And notice at lag 1, I got this right here. And actually, this is lag 2, where you see my mouse is. So I will miss what happened on lag 1, because lag 1 is actually being right here on the y-axis. So, unfortunately, I've made that mistake before. You got to be careful about understanding how that argument for par works, because you don't want to miss that first lag. Okay? And let's take a look at the ACF plot. Let's look at the plot of the data over time for the shiny F. Okay. So do we have non-stationarity in the mean based upon what you see here? There's definitely more evidence of it than what we had in the previous earthquake example. For an extended period of time, it seems like my mean is right about here, let's say. For an extended period of time is about here. And depending upon how you want to treat that there, which is around Christmas. It looks like maybe I have two means over an extended period of time. And what is the actual extended period of time? Well, it's about time point 10 to maybe time point 130. Okay, that's about 100 times, at least 100 time points. And so I think here, yeah, it looks like I'm having some non-stationarity in the mean. It's definitely not as clear as what we've seen in other cases where we have this general upward trend or downward trend. But I think something's going on here. And I would at least want to investigate that further. We will have some other techniques that we can use later in this course as well with this to make a final judgment. Actually, let's come back here. So we also have to think about non-stationarity with respect to the variance and autocovariance. Now, it's easier to think about this in terms of the variance. What do you think here? Do we have non-stationarity with the variance? And we're looking at variability over time. I have a little bit less variability there. Again, that's actually around Christmas, between Christmas and New Year's. I don't know, maybe we have less variability here, compared to some other parts. So I would definitely, start having some concern about non-stationarity with respect to the variance based upon this plot. Parts D parts D and E. Let's take a look at that. Not some groups picked up on this, but many did not. Notice this is a plot of the estimated autocorrelations. Notice that lag 7, 14, 21, 28, multiples of 7. We have these higher values. And I just want to point this out here is that this is common to see when you have seasonal data. What that means is that basically, let's say today, Tuesday, is dependent upon what happened the previous Tuesday. A little bit more, it's more dependent with respect to that than, let's say, Tuesday today with respect to Thursday of last week. This is what this is saying. So, this lag 7 would be Tuesday today, Tuesday of last week. This lag 14 is Tuesday today, Tuesday from 2 weeks ago, essentially. Or it could also mean Thursday of this week versus Thursday the previous week, Thursday the previous week after that. And that makes sense to have some kind of dependence like that over time, especially when you put it into context of, okay, these labs that are doing the COVID testing are probably not open on the weekends. Okay, let's talk about number 4 here. This is a minor thing, but it's something that you need to do. Whenever, let's say, we'll just do this. Suppose I have the time series denoted by A for some reason, and it's a time series variable. And let's say I'm at time t, and then for some reason I'm squaring it. Notice how the superscript is right above the subscript. It is incorrect notation to do this, or to do this. Subscript right below the superscript. Now, I understand why it's tempting to type out some notation like this when a superscript and subscript are needed. It's easy to do. But you got to use an equation editor then to do this properly. This is, if you were, for example, to, let's say, do some kind of report for your advisor so that you can get your master's or PhD, the advisor wouldn't like it. If you're trying to submit a paper to a journal and you were using this kind of notation, the journal would say, no, you can't do that. You got to use proper notation. Okay, that means you have to actually use an equation editor. Okay. So I think that's all I want to say about the project. I went a little bit longer than I wanted to there. Hopefully this gives you a little bit more background in terms of what my thinking was with respect to the answer key and why maybe at some points I took off points, or maybe even other points I did not take off, or other places where I did not take off points. Are there any questions about the project? Okay. Yeah.
So if non-sterility in mean is conclusive, then do we still need to look for non-sterility for variance?
Yes. And if you remember, there was a different solution for that, for non-stationarity in the variance. So, for example, you could look at a transformation of the response variable. Later in the semester, we'll look at other kinds of models, which are referred to as GARCH models, that help you to model the variance simultaneously in addition to, let's say, X of t. So you do need to still look for it. Typically, what's done yeah, I'll just leave it there. You do need to still look for it. Okay. Okay. So before we talk about project number 2, And I think that's the last thing that we'll be able to do here today. Let's take a look at the schedule for this course. So we're week 5. And so you might have noticed on week number 6, I have this TBD, to be determined. What are we going to do that week? I put that there because I was hoping to find a solution to a problem that I have. And I wasn't not able to figure out a good solution. So next week, I will actually be at a conference. It's a statistical conference, a conference on statistical practice. And this conference starts on a Tuesday and ends on a Thursday. I have never, ever seen a statistical conference that was completely in the middle of a week before. Usually it starts like on a Saturday and then, maybe ends on a Tuesday so that you don't miss the whole work week. Or, you're not like right in the middle. Or maybe the conference starts on a Thursday and goes through a Sunday. For some reason, and I know in the past this conference has been around a weekend, but for some reason this conference this year, Tuesday through Thursday. I looked for flights so that maybe I could still be here on Tuesday, or maybe I could get back early. Well, Thursday was out. I couldn't be able to do that because the conference goes till noon. And so I wasn't able to find a good flight on Tuesday. Maybe I could get there late. And so what this means then for you is that we're not going to have class next week. When in the past when I've had conferences, let's say if we would miss Tuesday, well, we'll just have our regular Tuesday class on a Thursday. But that's not going to work. I've even done teaching remotely, essentially from my hotel room. We can meet on Zoom and do teaching and have a class that way. But the flight times prevent me from actually being in my hotel room at exactly that same time, unless I actually go down a day early and pay $250 extra for another night of a hotel room, which I don't want to do. So we are not going to have class next week, unfortunately. And so to plan ahead and knowing that was probably going to be the likely result, I had made some small changes in our schedule this year so that the stuff that's the least important, essentially I removed. And so don't feel as though you're being shortchanged that, and I have one less week of class, one less week of material. The stuff that I end up skipping is not a big deal. Okay? One of the things that I am skipping is subsection 8 out of section 3. So if we look ahead now to week 7 and the information or the material that you need to go over. So subsection 8 talks about a way to estimate the parameters of an ARMA model, as does subsection 9. Subsection 9's methods are used much, much more frequently than subsection 8. So that's why I thought it would be okay to skip subsection 8. In fact, usually when I teach it, I just focus on the 9 stuff for most of the rest of the course. So when you go over the material, please skip subsection 8. Now, I still left my notes out there. So if you really, really wanted to see it, you could. And the main thing is that there's something called Walker equations that discussed in subsection 8. And my recommendation to you is if you ever see, when you do time series analysis outside this course, you ever hear somebody call or refer to Walker equations, that's the only time that you should go back to my notes. Otherwise, you'll be fine without that section. Okay? So also, as we look ahead here, notice there's no quiz then on week 6. There is a quiz, of course, on week 7. But notice where project number 2 is due. It's due March 7th. So this is the Thursday of week 7. So after today, there's one more of these regular Tuesday classes before that project is due. So to some respect, it's coming quickly, even though we haven't went over the project yet. So let's actually go over the project. And you'll see that basically you have enough background to do almost all of it. The stuff that you don't is in green here. Okay. So this project is in the same format as project number 1, working groups of up to 3. Now, when I was going over the project one last time, preparing for class here today, when I was doing this yesterday, going over the project one last time, unfortunately I came across a few typos. I did upload a new project that has everything corrected. I uploaded it yesterday evening. So if you downloaded it in the evening, yesterday, or maybe this morning, your project's fine. If not, I've indicated here where the typos were. I also have some stuff that just a little bit of some hints to help you out. Okay, so in problem number 1 here, we're going to be working with the earthquakes data again. And you've already plotted the estimated ACF, but I want you to do it again. And then also plot the PACF now for this data set. And put the two plots nicely side by side. This is done typically in practice because, again, we're using both of these plots to make judgments about our data, in particular, eventually, to choose a particular model to estimate. Okay. Subsection 6, and I kind of alluded to this before, actually shows you in R how to estimate this model. I'm sorry, how to estimate the PACF. And as you might expect, there's a function called PACF. It works very similar to the ACF function. Then, part B. Tell me what that second estimated partial autocorrelation is. State it. Do a hypothesis test for that partial autocorrelation. Subsection 5 talked about the process. Subsection 6 coming up then talks about here's the plot, here's how you make the judgment. Again, it works very similar to working with ACFs. Then part C. Now, based upon what you see in the estimated ACF and the PACF, suggests 2 possible models that could be used with this data. I purposely said 2 rather than just 1 because I want you to see that there can be multiple interpretations of these plots to make judgments about what will be an appropriate model for a data set. Subsection 6 gives you more background about how to make those kinds of judgments compared to what you've seen so far. In part D, finally we get to a point where we actually get to estimate a model. In this particular case, we are estimating what you could say is an ARMA 1-1 model, meaning P is 1, Q is 1. As you will see in subsection 7, we extend these ARMA models to be what are called ARMA models. So we put an I in there. You'll see what that means in subsection 7. And I forgot to put in there the thing that corresponded to the I. So we have a P for 1, a Q, or a P is 1, Q is 1. And this middle thing here is actually what we're going to call D. D is going to be the number of levels of differencing. So the I for ARMA, as you will see, corresponds to differencing. It helps you take care of non-stationarity in the mean. Number 2 then. This is a problem somewhat coinciding with what I was doing earlier regarding looking at simulating data with n equal 24. And then we also looked at n equal 1000 to see the differences. That was using plots of the x of t versus t. Now what we're going to do is we're going to have a time series model here, and we are going to now look at the ACF, the estimated ACF from the simulated data, and the estimated PACF from the simulated data. And we're going to compare it to what we would expect it should look like based upon, again, we know how to derive the ACF and PACF. So, in this particular problem, we're going to have an ARMA model that actually has P equal 1, Q equal 1. Here's my phi 1. Here's the theta 1. Make sure when you simulate the data using ARMA.sim, you get the signs correctly on phi 1 and theta 1. We're going to have a variance of 1 for the white noise part. First, with this model, tell me, is it causal? Is it invertible? Tell me why. So what you're going to have to do is essentially look for some roots of a polynomial. Part B, for this phi, for this theta, plot what the actual ACF and PACF should be. We've seen some functions already that allow you to do that. So it's just a matter of implementing those functions in R and plot them. Then C, with only a sample size of 25, using ARMA.sim, let's simulate the data from this model. Print the data, plot the estimated ACF and PACF, and then compare how well do these estimated ACF and PACFs compare to what is true, what is the true values. Do you think it's going to match up perfectly? Yes or no? Based upon what we've seen earlier today, do you think it's going to match up perfectly? Well, it wasn't a rhetorical question, but we can make it a rhetorical question, and we'll move on. Then we have some R stuff here. I want you to construct one function in R that basically does this process for us in terms of it can repeat the data simulation and this plotting process of plotting the ACF and the PACF. Run the function with n equal 25 and that same seed as what we had before to verify that indeed you get exactly the same answer. So now you have one function that you can use that does a lot of this stuff already. That's what we often do in R, is we constructed functions to automate what we want to get done. Then, using this function now, with these sample sizes, do the same thing. So with n equal 100, get the estimated ACF and PACF. Compare it to what the true ACF and PACF are. N equal 1,000. Get the estimated ACF and PACF. Compare it to what the true is. And then do it again for 10,000. So what this will give you, this particular problem, is a better intuitive understanding of how sample size can affect the ACF and PACF in terms of the estimated, and then thus how this can actually affect your ability to use the ACF, the estimated ACF, the estimated PACF to choose a particular model for an observed data set. That's the purpose of this. Okay. Now problem number 3 here. Suppose you have an ARMA 2-1. I want you to develop an expression that writes out an infinite order moving average with your coefficients denoted by these psi terms. You've seen examples like this in the notes, like with an ARMA 1-1. Now we have an ARMA 2-1. So go through the process to help simplify things. Once you see a particular pattern involving these psi's, just tell me what the pattern is. You can leave it in terms of the size. You don't have to get everything always in terms of the phis and the thetas. That's completely fine. Then part B. Well, let's put some numerical values in there. So I have a phi 1, a phi 2 because p is equal to 2. I have a theta 1 because q is equal to 1. Construct your own R function that does the actual numerical calculation using what you have found in A. So essentially for any phi 1, for any phi 2, any theta 1, this function is going to work. But I want you to actually run it with this, this phi 1, phi 2, and theta 1. It's going to calculate all these size. Then, part C, remember we have an actual function already that does the calculations for us. It's called ARMA to MA. Run that function with these parameters. Your value, you'll know that you got the answer right in A and B if you have your answers match up with what's in C. This is an illustration of something I think we talked about last time. How we have these tools that are available to us to kind of check our answers. Well, let's take advantage of it. And this is how you can do it. Now, some of you might be thinking, oh, you want me to write a function that automatically calculates these terms. I could go and take a look at the ARMA to MA function and just copy and paste that code into my own function, and I am done. Chris, you've made this too easy. Well, how would I actually see what's inside that function? What would I need to do? I could just simply type the function name, and it should give me the code for that function. Sorry, I didn't make it that easy. So this is what I get. What's this? What's the code of this function telling me? Does anyone know? I have a function called .call. Even if you take in Stat 850, I bet you would not talk about this. But it's something good to discuss here. And just for your understanding of how to use R. Does anyone know what .call does? One thing that might lead you to what the answer is. Notice we have the letter C there. Capital C. I know you're waiting for me just to give you the answer because you know I'm going to do it. Okay. So our functions are programmed in a way that it will often take advantage of the R language and do the computations. But at times, some of these computations can take a while to do. Or perhaps, maybe there's already other software out there that does the computations already. So why reinvent the wheel? So could we somehow then use some functions that have maybe written before in another language, or perhaps actually write our own function in another language that we know will run faster? So for example, if I were to program in some calculations in R and program them also into, let's say, C++, the C++ stuff will probably run much, much faster. I'm not going to get into the details about that, but there are just different levels of, you could say, programming languages out there. And much of what R has available to it, to us, I shouldn't say much, but some, is actually stuff that's been programmed in C++ previously or been programmed in Fortran previously. And obviously there's been stuff that's been programmed into more modern languages as well, but still R really relies on Fortran in C++. In fact, I believe the actual the way, I'm not going to go there right now. And so whenever you see a .call function, it's calling outside of R itself to in this case, a C++ function. I know that because it says C there. And so that's how the actual computations are being done. R takes the data that you pass into it, or the information that you pass into it, sends it out to a C++ function that comes with the installation of R. That function does its work, sends it back to R. Now, there are ways that you could actually see the C++ function if you want to. What you have on your computer is actually what's called a compiled version of that function, or executable, I should say. You can actually download what's called the source of R, which actually has all the C++ code, all the Fortran code, and any other languages that it uses. It has all that code there. And you can actually download that. And you can see how the actual computations are done for something that does the ARMA to MA. You don't need to do that here. But I just thought that this is a nice little thing to know about, that you might be frustrated, like, okay, where's the code? I want to actually see the code. And it's not immediately present. And that's why. It's because it's actually programmed in another language. Okay, any questions about that? Okay, so let's end with this then. Well, what's next in our class? So again, I'll be available for questions after class. You do have a quiz that's due at 8 p.m. today. On Thursday, I'll have my usual office hours, and then I'll be here for the help class at 9:30 a.m. Again, that might be a good time to get started on this project. Next Tuesday and Thursday, we do not have class. Please feel free, though, to post questions to our discussion board that might come up, especially about the project. I will obviously have computer access when I'm at this conference, and do know it might take me a little bit longer than normal to get back with you, especially if you post during the day, because during the day I'm in the conference, but in the evenings, if I remember right, there's no conference activities that are planned, so I should be able to get back with you then. So our next regular class is Tuesday, March 5th. It's subsections 6 through 9, but skip 8. This corresponds to, in our book, these particular sections. So if you're reading the book at the same time as you're going through this course, that's what you should read. And finally, we're going to get to the point where we can estimate one of these models. Note that the authors, because they don't like some of the ways that in the default installation of R, they don't like some of the ways that the estimation functions work. And so they basically kind of constructed their own functions based upon the functions that are already in R. We will not use their functions that they advocate using. Also, in this section, we're going to talk about making inferences about like phi 1 and phi 2. And we're going to use basically what are called, referred to as large sample distributional approximations. The authors say another way to do this is to use a procedure called the bootstrap. I will not talk about the bootstrap in this course. I don't know, maybe if we end up having time at the end of the year, I can talk about some. I actually used to teach a whole course here at this university on the bootstrap, and there are some interesting things that can be done with it. But most likely we will not. We'll probably talk a little bit more about project number 2 on March 5th as well. The project is due Thursday, March 7th at 8 p.m. And take a look at this test day. So 1 week from tomorrow. 1 week. It's 1 month from tomorrow. Okay, so it's coming up. Do note that obviously we have this 1 week off because of my conference. We also have spring break off. So there isn't that much more material left before test number 1. Okay. Are there any questions? Okay, and that's it for today.